Сейчас мы послушаем лекцию сэра Рождера Пенроуза, математического физика, которого отличает от многих других математических физиков 20 и 21 века невероятно счастливые отношения с реальностью. Всю свою жизнь он опирается на чрезвычайно сложную абстрактную математику, но так сложилось, что 4 или 5 раз его предположения, которые на первый взгляд выглядят чрезвычайно странными, удивительными, экстравагантными, предположения о том, как устроен мир, получали экспериментальное подтверждение во всяких наблюдениях. Так было с его представлениями о черных дырах, так случилось с его одной совершенно теоретической работы, касающейся мозаики, которую можно выложить из двух элементов, которые имеют поцелующую симметрию. Существенно позже ее наблюдали в структуру, которая называется квазикристаллы. И сегодня мы услышим еще об одной области его интересов, которая исходно абсолютно абстрактная, абсолютно теоретическая и приводит к совершенно фантастическому предположению об устройстве мира и о его истории, в которой он активно искал сотрудничество с астрономами, которые занимаются наблюдениями за космосом. И так случилось, что с некоторыми из них у него получилось очень продуктивное сотрудничество, и он и его коллеги видят в этом подтверждение тому, что так действительно устроен мир. Выясняется, что в отличие от многих других математических физиков, реальность чрезвычайно важна для него, и реальность платит ему взаимностью. Сэр Рождер Пенроуз.
Well, it's a great pleasure for me to be back in Moscow. The last time I was here was in 1971, I think. And I also went to what was then Leningrad to see my grandmother's house. She lived in St. Petersburg in the late 1800s, and then went to Switzerland where she met my grandfather, and unfortunately she never returned. But it was nice to see her house. Okay, so let me give you the title. I see you have it in Russian. The title is my title in English, which I hope is a translation of that into English. It's here. Seeing through the Big Bang into another world. Now, you might believe me or might not. I do mean what I say. This, another sort of milder title here, which is my official title for this subject, which is Conformal Cyclic Cosmology, which in English abbreviates CCC. That's nothing to do with the Soviet Union. And this is a basic introduction where I'm not going to give you any of the equations. So I hope that's all right. Now, before giving you this scheme, I used to lecture on this under the title of sort of outrageous new cosmology or something like that. And after a while, I got used to the idea myself and I stopped calling it outrageous. So that's partly because I suppose familiarity means that I didn't think of it as so outrageous as I did originally. But first of all, before telling you my cosmological scheme, I want to tell you the conventional picture of the universe, and to draw the universe, as is what I usually do, I shall give you a space-time picture. So you see time is going up the picture like this, and you have to think of, well, the Big Bang is the initial point here, big explosion, and the universe expanded outwards. So as time goes by, think of sections through it like this as representing space at any one time. You may ask what all this funny stuff is at the back. And somebody, I forgot to explain in one lecture I gave, and somebody said, why has the universe got a hole in it? Well, the reason the universe has a hole in it in this picture is I did not want to bias the situation with regard to whether the universe is open or closed. It's easier to draw it if you imagine it is closed, so you think it's going all the way around here, but maybe it's not, and maybe it's open, and so I have these sort of wiggles going out there, and who knows. For the purposes of my talk, it does not matter whether it's open or closed. However, we do want the Big Bang, we do want this expansion here, it slows down a bit, and then we have this accelerated expansion. This accelerated expansion got the Nobel Prize. Well, I mean, the physicists didn't get the Nobel Prize. The physicists who observed this expansion got the Nobel Prize, not the last year, but the year before that, the Nobel Prize for Physics. And this was not expected by them, and they tended to call it some mysterious dark energy. It's referred to as dark energy. However, to people who've been working in cosmology for many, many years, it's the sort of thing one would expect. If there is this term in Einstein's equations, there's a thing which we call lambda, I suppose we call the Russian for L, whatever that is, the thing which looks like your Russian L, and we call that lambda, and this is the term that Einstein introduced into his equations in 1917 for the wrong reason. He wanted to have a universe that was static, was not expanding, just stayed there forever, and he needed that term in his equations to make it stay forever. But then shortly afterwards it became clear that the universe was not static and was expanding, and so Einstein then changed his mind and withdrew his cosmological constant, this lambda thing. He withdrew it and said this was his greatest mistake. However, it turns out that even Einstein's big mistakes, this one in particular, turned out to be true. So Einstein was right, that there is something like his cosmological constant, or lambda, or dark energy, or whatever you like to call it, which seems to be coming into play. We are, I should say, this is the history of the universe. We're somewhere up about here, where we're beginning to see this exponential expansion taking place. Now, there is one thing about this picture. It's supposed to represent our conventional present view of the universe. You might say, where is inflation? There is a thing called inflation, which is supposed to have taken place in the very, very, very early stages of the universe. Now, there are two reasons I have not indicated inflation in this picture. One of the reasons is, well, maybe I have. Because if inflation took place, it would be hidden right in that little spot at the beginning, and you wouldn't see it at all on the scale of this picture. So maybe inflation is in the picture, and you just don't see it. Well, there's another reason I haven't drawn it, and that is I don't really believe it. I'll come to that in a minute. But first of all, can we perhaps have a look at it? And in order to have a look at it, I'm going to need a very powerful magnifying glass. Here is my magnifying glass, and so I'm going to take a look at it and see what it looks like. Okay. So here is what it is supposed to look like. I should start from here. This is the handle of the magnifying glass, and there is inflation. Said here, inflation, Big Bang is before inflation. So this is the conventional view. If you look at any modern cosmology book, whether it's a popular book or a serious scientific book, they will talk about inflation as though it really took place. Now, one thing I want to point out about this is it's very much like what we see for the exponential expansion of the universe in the remote future. So this is our remote future. And this is supposed to have been a phase which took place very, very near, immediately after the Big Bang. A very, very tiny fraction of a second after the Big Bang. According to the inflationary model, this universe expanded like that. Well, I was never very happy about this idea when I first heard of it, partly because it was supposed to do various things which I didn't believe it did do. I thought, no, it doesn't really do this. I won't say too much about that. I'll mention a little bit later the sort of reason I didn't believe that. But later on, there became good reasons for why inflation might have been there. And if you don't have inflation, you have to have something else which serves the purpose of inflation. And I'm pointing out this exponential expansion being very similar to what we see here. And the picture that I want to present you, actually maybe it's not there, but in the picture I want to present to you, it is in a certain sense there, but it's not after the Big Bang, it's before the Big Bang. So that's a strange thought, and let me try and explain what I mean. In fact, that's more or less the purpose of this talk. As a lead up to that, I want to show you two mathematical tricks. Now these are just tricks which, as a mathematical physicist interested in cosmology, I've been applying one way or another for a long time, very many decades. One of them is to take the remote future and squash it down. So I squash it inwards until it becomes a finite boundary. Now, in order to explain a bit better what this is, let me show you a picture which may be familiar to some of you. This is a picture due to the Dutch artist M.C. Escher. It's called Circle Limit 1, and it's a picture of what's called hyperbolic geometry. Well, I noticed Lobachevsky here is the one who thinks I'm in Russia, I should certainly mention him here. This particular diagram is due to Beltrami, although people call it the Poincaré disk. It's one of these things in mathematics. Often the name attached to something is not really the name you should be attaching to it. Beltrami was an Italian geometer, and he devised this way of representing this geometry. Now, I'm not concerned with that geometry here. What I am concerned with is the kind of picture that we have here. It's what's called a conformal picture. You see these fish-like creatures, they inhabit this world. This is the entire world of these fish, right out to infinity. That's the entire world. Not just part of it, it's the entire world. That's the entire Lobachevsky geometry. Now, these fish in the middle look as though they're bigger than the ones that you get near the edge. But you have to imagine that if you were one of these fish, you would be just the same as one of these fish. And if you happen to be this one living here, you would think you were just the same as this one here. So the geometry gets squashed as you go out to the edge. But the particular character of the squashing is what's called conformal. Now, what that means is that angles, like the beak of this fish, I don't quite know why a fish has a beak, but never mind. The beak of the fish has the same angle wherever you see it. More seriously, notice the eyes of the fish. They are circles. And those are exact circles, no matter how small they seem to be near the edge. So the representation of the fish, according to this geometry, is a conformal representation. It means that angles are correctly represented, even though sizes are not. So when they look small to you or to me here, you have to imagine they're not really small. It's the representation which has squashed them down in this conformal way. Conformal means that as it gets squashed, these small shapes get preserved or angles get preserved. So when I do this squashing here about infinity, I squash infinity down, it is the same sort of trick as is used here. So Beltrami used that trick in this picture. I'm using it to squash down infinity. Now I'm using the trick in the opposite way to stretch out the Big Bang. So I'm doing two things. One is to squash infinity down, and that makes a boundary, like the boundary you see here. You see the boundary is a circle around the edge, which represents infinity. In the same way, I'm representing the infinity here as this finite boundary here. And these are what I call conformal. And I'll say a little bit more about that later on. Okay, so I'm squashing infinity down and I'm stretching the Big Bang. Now this stretching has the advantage that whereas it is what's called a singularity, a singularity is a place where all your equations go wrong. That's the idea. Things go infinite. Near the Big Bang, you have infinite temperatures, you have infinite densities, you have infinite curvatures of your space-time. And so Einstein's equations just say, well, we give up. So that's the normal way that people think about the Big Bang. They think the Big Bang was a place where the physics simply invented itself or something like that. So it's not really where you're allowed to use the ordinary equations, they go wrong. Okay, but the trick here is to stretch it out so maybe you can use ordinary equations. That's the idea. So those are just two mathematical tricks. Now those two mathematical tricks, I want to say something more serious about them. That they're not just tricks, but in a certain sense, they're real. Not only are they real, but when I squash the infinity down and stretch the Big Bang out, I can stick that onto another model of the universe, and I keep on going. Now, I'm going to use this following terminology. I'm going to call this an eon. I'm not saying this is the whole universe now. I'm saying it is one eon. In English we spell it A-E-O-N. I don't know Russian word for that is, but I'm sure the translator does. Here we have an eon, which is represented by that finite stretch of an infinite succession of such things. So now you have to imagine that the entire universe, which is this infinite succession of eons, well, it's only one segment of it, which is the universe that has been talked about previously. And when I say, what about inflation? Well, you see, this is our eon, say, and we're somewhere around about there, somewhere around about here, we're about there, actually, pretty accurately in the picture. Well, where is inflation? It's the eon, it's the infinite future of the eon prior to ours. So there isn't any inflation as such, but there is this exponential expansion of the previous eon, which plays the role of inflation in the current cosmological picture. I should say that this particular idea was actually due originally to an Italian, very well-known Italian physicist called Veneziano, who is one of the originators of string theory. Now, I'm not using string theory in this picture at all. There is no string theory in what I say here, so that may be a relief to some of you. No string theory. He had a model which did involve string theory, so it was not really the same as my model, but the idea of having an inflation which was really an exponential expansion in something before the Big Bang was basically due to Veneziano. Now, there is something else I want to say about these two mathematical tricks, and that's important in the whole scheme. One of them is the future trick works under very general circumstances. There's basically a theorem, a mathematical result due to Helmut Friedrich, a very good mathematical physicist, a German mathematical physicist, who really showed that if you've got this exponential expansion, you can pretty well do this trick. The other trick has a very different character. It's an extremely strong restriction, and it suppresses gravitational degrees of freedom. I'm going to say why that's important shortly, but the idea that it does this is due to my colleague Paul Todd, who was using this device here as a way of characterizing the Big Bang. So let me say a bit more about that, because that is a feature of the model which is crucial, which is very central to the whole scheme. And it's a way of addressing one of the most important laws in physics. What is this law? Well, it's the second law of thermodynamics. So here's the second law of thermodynamics. There we are. But I want to stress something else about the second law of thermodynamics. You see all these question marks all over the place. The second law of thermodynamics is in some sense one of the most natural things we have. It tells you that randomness is increasing all the time. Maybe you're used to this idea of randomness increasing all the time. We are used to it in our country too, so don't worry. It's a familiar phenomenon. But I'm saying that there is a deep mystery in the second law of thermodynamics. And I want to try and explain why there is a deep mystery. It's one of these things which is hardly ever mentioned by cosmologists, and I'm very puzzled by this. So you'd think that cosmologists would be worried by this mystery. Let me tell you what the mystery is. Now, first of all, to give you some idea of how the second law operates, I have here a cartoon of perhaps rather too familiar phenomenon. We have a glass of wine which had been perched rather unstably on the edge of the table here, and it tumbled off, the wine spilled itself into the carpet, the glass smashes like this. Now I'm going to treat this as something in ordinary Newtonian mechanics, and now I see to put some more pieces of paper over it. The secrets are being revealed in the class. Never mind, it's not that important really. Anyway, if you think of this as something happening in Newtonian mechanics, now the laws of Newtonian mechanics are symmetrical in time. If you run the clock backwards or forwards, the laws are just the same. It doesn't make any difference which way the clock works. However, you might say, well, this is something which is happening according to the dynamics of Newton. Well, you can bring in relativity, you can bring in quantum mechanics, there's a little issue there, but you can bring in pretty well all physics, and it's still reversible in time. So that means that if this, left hand, middle, and then right hand, are things which could happen according to the dynamics, then that, the last one and the middle one and the first one, could also happen according to the dynamics. So if this is possible in one direction, left to right, then right to left, is also possible. Why do we never see the other direction? Well, the second law of thermodynamics says there's a thing called entropy, and entropy is a measure of the disorder of the system, and the second law tells you that the disorder is increasing all the time. So this left, middle, right is consistent with the second law because the entropy is increasing, whereas right, middle, left is inconsistent with the second law. But, well, how do we understand that? Why is it true, and so on and so on? I mean, if the laws are symmetrical, why do we have asymmetrical occurrences like this? Well, I'm going to show, this is one of the, perhaps the most mathematically sophisticated thing I'll say here. There's a thing called phase space. Now, what is phase space? You have to imagine that this picture, I've only drawn it rather crudely, but of course there are lots and lots of particles involved, and the particles might be one place or another place without making much difference. You see, maybe there's a molecule of air over here, or it could be over here or over there, and there could be another one there, and so on. You're not interested in that. You're really just interested in average quantities like the density, the temperature, the general direction of flow, and things like that. And the chemical composition of the wine, and that sort of thing, which describe the situation generally. But you're not so interested in exactly where every particle is and exactly how it's moving. So what you do to talk about the entropy, roughly speaking, let me tell you roughly first, that there are lots of particles, and to make up this picture, there may be many, many ways of doing it. As the entropy increases, they get more and more ways of doing it, more and more and more ways over here. So as you move from left to right, to make up the picture that you see, there would be many, many more ways of doing it. Well, we understand that in physical terms by talking about phase space. Phase space is a space with a huge number of dimensions. How many dimensions? Well, let's suppose there are a zillion particles here. That's not a proper English word, but just lots and lots. A zillion particles here. Each of those particles has a certain position. So there's 3 zillion numbers you need to characterize all the particles, and a certain motion. Well, there's a momentum to it, a velocity. Technically, you want the momentum, which is the mass times velocity. So you have 3 numbers for the position, 3 numbers for the way it's moving, the momentum, and so 6 numbers per particle. So if there are a zillion particles, you have 6 zillion coordinates needed to describe this. So you've got to imagine this space here, that's the phase space, is 6 zillion dimensions. Well, I haven't drawn it very well, have I? I've just drawn it as though it had 2 dimensions, but that's the best I can do. You have to imagine it has 6 zillion dimensions, and each point in this picture represents the entire situation in here. Where all the particles are, what kind of particles they are, and which way they're moving. All that is included in the single point in this picture. So if I see a point here, that's telling me everything about that. Now, you notice these spaces divided up into little boxes here. The idea is these boxes are what are called coarse-graining boxes. That means that all the different points in the same box, the one marked yellow here, you see, all the different points in that same box look the same in this picture. So the motions of the gas generally, although the detailed positions of the particles will be different, and that's all the different places in that box, but the box itself labels the general picture you see. Now you see what's the volume of that thing, so the high dimension volume, that's the V in here. You take the logarithm, don't worry about that too much, and then you don't worry about this either, that's Boltzmann's constant, and this is the thing called the entropy, which is S for some reason. Okay, so the entropy is just the size, and when in terms of logarithms, the size of this region, which tells you how many ways of making this situation here. Now, there's two things which are a bit misleading in the way I've drawn this, and I can't get away from it. One of them, I haven't used enough dimensions, and the other, which goes along with that, is that you see some of these regions are a bit bigger than others, and some are a bit smaller. You've got to think of the ones that are bigger are absolutely stupendously bigger. The ones that are smaller are absolutely tiddly in comparison. So you have to imagine that. Now, how does the evolution go as you go from here, left to middle to right? Well, this point winds this way, and the boxes get bigger and bigger and bigger, and as they get bigger, they get stupendously bigger as they go along. Now, the thing is that as you find your way from here into the bigger one, the next step is going to be the much bigger one. You're never going to find this little one again. So that's, if you like, why the entropy goes up. It's a perfectly... I haven't used much physics. I've just waved my hands around. And basically that's the idea, that because these things are so different in size, that the trajectory here, which represents the evolution of the system, is bound to be something in which the entropy goes up. So that's the idea. Is that all there is to the second law? Well, there's a bit of a catch to it. How do I deduce something asymmetrical from symmetrical laws? And you may well be puzzled by that, because it's really because I asked a question in a particular way. I said, if you start with this situation here, what's the most likely thing to happen to it? Well, the entropy is going to go up, and it does that, and that means the curve gets bigger and bigger volumes. But suppose we ask a different question. How did the glass get there in the first place? And then I go back to my phase space picture, and I say, well, the most likely case was a much bigger volume before that, and a much bigger volume before that. So that tells me the most likely way the glass got there in the corner was that it started as a great mess on the floor. Suddenly the glass jumped up, assembled itself, and all the wine sucked itself out of the carpet, stuck in the glass, and perched itself on the edge of the table. Well, that's obviously completely wrong. The right answer is that somebody who had been drinking too much of this had staggered up to the table and perched it rather badly on the corner. And that is consistent with the second law, because even though that person may have been rather drunk, that person had a much lower entropy, much more organized than the stuff around. So we have a puzzle. See, my argument that I just gave you the wrong answer, the retrodiction, is this green curve. What really happened was that the second law held right back, and the curve really did this. This curve represents the entropy plotted against the time. Time is going off to the right, and the entropy going up is the prediction. And the bad retrodiction is the curve going up in the past. That's wrong. What really happened is it came up from the past. So there's something missing. There's something which pulled this curve back down in the past. And what was it? Well, let's go back and have a look earlier. Well, I have to bring my other transparency in here. And if you go back and back and back, you find the Big Bang. So in order to make sense of all this, we have to imagine that the Big Bang was something of very, very low entropy, very, very organized. Okay? Well, there's nothing wrong with the logic here, I assure you, is completely correct. that the Big Bang must have been something highly organized. Either we did not, otherwise we would not have had a second law of thermodynamics which stretched its way back to the Big Bang. Okay, but what do we know about the Big Bang? Why do we think there was a Big Bang? Well, one of the reasons we see is the universe expanding, but there's a much more direct piece of evidence for the Big Bang, and that is the microwave background. This is radiation coming from all directions in space. That got a Nobel Prize twice I should say, in two separate occasions. First for the discovery and secondly for details about it. Now, it's sometimes called the CMB, cosmic microwave background. Now, I'm going to tell you two things about it. Both of them very important in what I want to say. The first thing I want to tell you is about this curve. Now, this curve represents, I should say that the cosmic microwave background is electromagnetic radiation. It's light, if you like, well, it's microwaves actually. That's why it's called microwave background, like in the microwave oven. And here we have the intensity. You see, this curve here represents intensity going up, and these are the different frequencies of the radiation. So as the frequency goes up, here we go like this, you see the intensity going up and coming down again. Now, there's a solid line here, and that solid line is a famous curve due to Max Planck, which started off quantum mechanics, basically. It's called the black body spectrum. And, well, let me tell you something about the black body spectrum. Before I do that, I want to say something about these little lines here. I should say that this is quite an old slide, and I think maybe the observations have improved somewhat since then. But even with this old slide, these lines going up here are error bars. So you see the observations may have a certain scatter about the curve, but they are exaggerated by a factor of 500. So even the worst one down here, you have to squash that down by a factor of 500, and you see that the errors are less than the width of the incline. So you have an extraordinarily precise agreement between the observations given by the limits of these error bars and the Max Planck curve. Now, what is the Max Planck curve? It's what's called the black body spectrum of thermal equilibrium. Now, what is thermal equilibrium? Well, I refer you back to my picture, which I just gave you a minute ago. Here's the picture. Thermal equilibrium, I've got drawn here. It represents the volume, the coarse-graining volume of by far the largest size of all these boxes. It's so big normally that it's bigger than all the others put together. And this represents where you end up. It's the maximum entropy state. It's where things go when they're left to. It's the maximum entropy state. Well, you might say, isn't there something a bit fishy going on here? Because didn't I say that you go back and back and back in time until you get to a maximum? That doesn't make any sense at all. It looks like a profound contradiction. Well, it's not quite a contradiction, but it is a serious point, and one of these points which I often puzzled about why cosmologists don't worry about it more. It seems to me a very deep point that we are having to understand here. Well, there are various things you might think. Well, you might say, well, the universe was very small in those days, maybe there wasn't much room for much entropy. That's just not right. There were as many degrees of freedom available then as later. So that's not the right argument. Let me give you the right answer. The right answer has to do with something else that we see about the black body radiation. Two things I said. One is this curve. The other is that it is very uniform over the whole sky. Well, there is a slight non-uniformity, but that can be explained, the major non-uniformity can be explained by the fact that the Earth is moving through it. And that means that in the direction in which the Earth is moving, it's slightly warmer, and the direction we're moving away from, and I don't know which way it is, but I get it right, maybe it's that way. The other direction, it's slightly cooler. You just correct for that, and then you find that it is very, very uniform over the whole sky. It's so uniform that the deviations from constant temperature of the sky are something like about a part in 100,000. So very, very uniform temperature. Okay, bear that in mind. That's telling us that the universe, as we go around, is very, very uniform. Okay, well, let's see if we can understand that. Let's imagine a gas in a box. And if you have a gas, which you might start off by sort of boxing it off in some corner. Maybe you have a little box there, and then you release the sides of the box, and the gas starts to spread out through the box. So you see that here the entropy is increasing, and it's getting more and more uniform. Again, that seems to be a paradox, because not only is the Planck spectrum telling you that you've got maximum entropy, you've also got the gas spread out uniformly over the whole sky, in other words, over the whole universe, if you like, in very, very uniform. Now, the thing is, if you want the answer to this paradox, as it seems, this is the answer, I'll tell you. You see, time increases, entropy increases, the gas gets more uniform, but let's think about something else. I'm going to think about gravitating bodies. So let's have an absolutely huge galactic scale box, and these are stars or something like that running around and attracting each other by gravity. Well, if you start off uniform, it will start to clump. As the gravity starts to take over, the stars get more clumped and clumped and clumped. Ultimately, they may well form into a black hole, which represents a huge increase of entropy. We know that now from the Bekenstein-Hawking formula, which gives a measure to the entropy in a black hole. And it tells you this is a vast increase in the entropy. But even if you don't have a black hole, this represents a huge increase in entropy. But this is entirely in gravity. So what we see in the early universe is a combination of that picture and this picture. You see uniformity, and as far as the matter and radiation are concerned, yes, it's the Planck spectrum. That tells you it is thermal equilibrium, pretty well. Thermal equilibrium, maximum entropy as far as the matter is concerned. But notice that the uniformity tells you that it's low entropy in gravity. So what you're seeing is a combination of those two aspects of the physics, and the lowness of the entropy is entirely in gravity. And that's a very remarkable thing. It's not just that the entropy was low at the beginning, which we need for the rest of physics, but it's low in a very, very special way, that it's gravity which somehow was not activated in the early universe. And it has seemed to me this is a basic fundamental problem of cosmology that is hardly ever addressed. You see, I often see things like what are the big puzzles of cosmology, and very often all sorts of things are mentioned. What is dark matter, what is dark energy, what is some numbers or some other numbers. But this one's hardly ever mentioned. I should also stress that this is not only what we seem to have from observation, but it's also why we're all here. Well, one of the reasons we're all here. And let me just give you another cartoon here. Why are we all here? Well, we're here largely, well, I don't know about the sun just in the last few days, I don't know. There was more sun in St. Petersburg than here, but we know there is a sun out there somewhere. And that sun is hotter than the background sky. So you might ask, well, what does the sun do for us? And people quite often say, well, we get energy from the sun. But that's not really the whole story, as Schrödinger has pointed out very clearly. Because, for example, suppose the whole sky was at the same temperature as the sun. It would be totally useless. We gain energy from the sun, if you like. It's not energy we gain from the sun because, okay, what happens in the daytime? Well, we get these photons coming from the sun. What happens in the nighttime and also in the daytime? They just go back out again. If they didn't, the Earth would simply get hotter and hotter and hotter. And, okay, it does. Global warming, despite the weather, global warming is happening, and it is warming up the planet. But that's a tiny effect by comparison with what I'm saying here. That pretty well all the energy goes back again. But it goes back again. You see, energy is conserved, so as much energy goes back into space from the Earth as comes in from the Sun. Now, the point I'm making here is illustrated by the many, many different arrows here representing lots and lots of photons going away and the rather few coming in from the Sun. Well, that's because the Sun is hotter than the background sky, which means its temperature, that is the energy per photon, is much, much greater as it comes in. These photons are higher frequency, and by Planck's E equals h nu tells you that these are more energetic individually. So that from the Sun, we get relatively fewer photons, which are individually more energetic. Going back into the dark sky are far more photons, individually of lower energy. And that's the key point. Since there are many, many more photons going away, that means many, many more degrees of freedom going out than come in. That means higher entropy. So the energy going out in high entropy form comes in low entropy form. As I said, that was the point Schrödinger made, which is a key point that most people seem to miss. So the point about life on the planet, well, you see, you get it all from the plants. The plants are clever enough, the green plants are clever enough to convert these high energy photons into low energy photons and use that to build their substance up, and that's how they keep their entropy down. Well, animals eat plants, and we eat animals and plants and so on, and that's how we keep our entropy down. So the point of eating food is not to get energy, because that just makes us fatter and fatter and fatter, that's no use. The point is that we get energy in a low entropy form and then we expel it back again in a high entropy form. So that is the key thing. And the question is, what about the Sun? Well, okay, there are all sorts of things about nuclear, thermonuclear energy and so on and so forth. The key point about the Sun is it's there at all. And it's there because it got gravitationally clumped out of what was previously more uniform distribution of gas. And as it clumped, it got hotter and hotter. The role of the thermonuclear forces is actually to slow down the contraction. So if there weren't any such things, the Sun would just get hotter and hotter and hotter, much too hot in fact, and it wouldn't last very long and it would die off. So the thermonuclear reactions are important, but the key point is that the Sun is there at all, and it's there at all because it's a hot spot in the dark sky, that's just what I'm saying here, and it comes from gravitational clumping. So it's just the fact that I've been talking about here. We're taking advantage of the clumping of material, and that's what we live off. That is absolutely crucial. Okay, so that's the key point. Now I do want to say something about the maximum entropy state we seem to see here, is when the clumping reaches its greatest effect, which is with a black hole. So black holes are going to play a big role in what I want to say here. And I have therefore a picture of a black hole, and like so many of my pictures, I'm afraid it's a space-time picture. Sorry about that, but it's sort of handy to have that. Don't worry too much about the picture, except I'm going to explain what these cones are doing. Here we have material collapsing in with some star or something which just got a bit too massive and collapsed. And then we have these things called light cones. Let me tell you about the light cones, because they are important. Space-time, well, it's four-dimensional, we get away with thinking it's three-dimensional as we do. One-dimensional time and the rest space. Now, you must imagine that this space-time has sort of conceptually painted on it at each point one of these little cones. Now these cones represent what light would do if there were some there. So let's imagine there was a flash of light here, and here I have a spatial picture, so this is a full three-dimensional picture, if you like, for space. There is the flash of light. That is the next moment represented through this section through the cone, and this is the moment after that. So it's got up to there, and this thing keeps on going. So this flash of light expanding outwards, represented by this cone in space-time. As I say, it's only a conceptual cone. It represents what light would do if it were there. It needn't be there. The cone is conceptually there all the time. There's also a past cone. This is a future cone with a plus sign. There's a past cone which would be light converging on that point, which is not likely to happen in actual fact. Now you have to understand, here we have relativity theory, both the special theory, where there's no gravity, and you imagine that all these cones are uniformly organized, and we have here massive particles will have what are called world lines, which are always within the cones. Now, a massless particle, a photon, which has no mass, has a world line which is along the cones. So that's the way it works. General relativity, well, it's just the same, except that these cones are now not uniformly arranged. Again, massive particles have world lines within the cones, photons or massless particles along the cones. And this is illustrated in the picture here, and if you want to follow through the picture, you can see why you get trapped if you fall in, because these cones are all, the outside edge of them becomes vertical in the picture, so there's no way, once you're in here, you can't get out without violating the rules. So that's rather unpleasant if you find yourself inside a black hole. We have this nasty thing in the middle, the singularity. Remember, we had singularities before for the Big Bang, but now I'm going to put the singularities in for the black hole as well. To get us a more complete picture, there they are. Well, there are probably lots more of them in the picture than I've drawn, but they form at certain stages and then they keep on going. Okay, so this is now a more conceptually precise picture than we had before, and we have two kinds of singularities. We have the singularity of the Big Bang, and we have the singularities in black holes. Now, in the early days when people were worrying about these things, they kept on saying, well, one's in the future and the other's in the past, and they pretty well like each other. But there is a crucial, huge difference. And that is that the Big Bang is in some sense a low entropy singularity, a very low entropy singularity, and the singularities in the black holes are very, very high entropy singularities. So whatever theory you have to try and explain whatever physics you need in order to talk about black hole singularities and Big Bang singularities, you have to come to terms with this extraordinary difference that you get. They're qualitatively similar in a sense, but they're also extremely different. Now, I want to give you one of the reasons why I don't believe in inflation. Well, it might be there, but it's not an explanation. You see, sometimes people say, well, the reason the Big Bang is so uniform is that there was inflation and it stretched everything out, and if it was all wobbly and wiggly, then it would stretch out and become flat. But it never seemed to me that was a good argument. Because if it was a good argument, just imagine, I'm not saying the universe is going to contract like this, just imagine it did. And suppose it contracted, and rather than the entropy increasing, you see, which it does here, suppose the entropy is increasing now, so you get black holes forming, you just have to wiggle it a little bit, and you get black holes forming, and then they form a great, incredible mess at the end, and you can put inflation in as much as you like, and it doesn't happen. You're going to get an incredible mess of a Big Bang, that is to say, a big crunch, is what we normally say here, a big crunch, incredible mess, which if that had been the beginning, far more likely, incredibly more likely, but it wasn't like that, it was like this. So there is the big puzzle. Why? Well, before we try to answer why, I'm going to address the question, what is it like? And I did tell you before about Paul Todd's proposal. Let me show you a bit more about that. This is the Big Bang must have been subject to a huge constraint, and you can work out how huge this constraint was. How unlikely was the universe in the form that we actually find it, as opposed to all the other possibilities. Well, you can work this out by just more or less doing the thing I was telling you. You work out the entropy here by working out, taking the entropy of a black hole and then seeing what it would be if everything forms a black hole. And that's a fairly straightforward argument using the Bekenstein-Hawking formula. And what you find is the unlikeliness of that Big Bang is something like 1 in 10 to the power 10 to the power 124. Now that's an absolutely ridiculous number. You see, 10 to the 124, well that's 1 followed by 124 zeros, and it's that many zeros here. So that's big. Very, very big. In other words, this is unlikely. Very, very unlikely. So, how do we say it? Well, I had various ideas. I think I call it the viral hypothesis. Fortunately, I don't have to tell you what the viral hypothesis is, because I'm going to use Paul Todd's proposal that we introduced in 2003, which is more or less what I've just told you before. That is, you consider that the Big Bang was of kind, as indicated in my previous picture here, was of a kind which, if you stretch it out, then it would be a nice smooth initial boundary. So that was his idea. So well, let's say, as a hypothesis, that the way in which the Big Bang was special was that if you stretch it out, it's nice and smooth. And that is exactly what I'm going to do. I'm going to try and pretend that the Big Bang was special in that very particular way. And this is the mathematical trick, which I mentioned to you before, about stretching out the Big Bang. It's a huge restriction on possible Big Bangs, but it seems to be a good candidate for what it was actually like. Now, that's mathematics. What about the physics? Well, you see, it's even, maybe there was something before it, because have a boundary which just sort of starts like that is a bit of a funny idea. Maybe there was something going on before it. Well, I think the sort of thing people would have thought of is maybe there was a big crunch before it and then it expanded up. But that's not going to work, because remember, that big crunch was a great mess. And so if you have a second law of thermodynamics in this previous thing here, it's going to produce a great mess, and that's not going to give you the smooth initial step you need over here. So that doesn't work. Now what is it that's down here? Well, is there anything down here? Well, I'm going to say a bit of physics here. See, near the Big Bang, temperatures get so high, far higher than the temperature in the LHC. Remember the Large Hadron Collider? There is this claim that they may have found the Higgs particle, perhaps they have. In fact, I'm going to take that kind of viewpoint, that when the temperatures get hotter than that, there is in effect no mass. You see, it's supposed to be this Higgs particle or Higgs phenomenon, Higgs mechanism, which gives mass to particles. But when the temperature is bigger than that, there is no mass. So that the particles very close to this thing are, in effect, particles with no mass. Now, why is that important? Well, I'll come to that in a second, but before I do that, let me talk about the top end of my picture instead. Remember that I wanted to stretch out infinity, so we have to think about what the future is like, and we use Mr. Friedrich's theorems and so on. Well, remember there are a lot of black holes around, and those black holes are going to cause a bit of a mess. However, Stephen Hawking comes to our rescue again. Hawking radiation. Well, you see, according to Hawking, black holes are not altogether cold. They have a temperature. They're hot, you see. Black holes are hot. How hot are they? Well, the temperature depends on the size of the hole. If the hole is bigger, the temperature is smaller. If the hole is smaller, the temperature is bigger. What are the smallest black holes that we have any reason to believe in? Well, they're likely to be the collapse of stars a little bit bigger than the sun. Maybe 8 or 10 times the mass of the sun. Sun won't be a black hole, but if it's much bigger, it might. And those are the hottest black holes around. How hot's that? Well, you have to think, sort of, to get a rough idea, think of the coldest temperature ever being made in the laboratory on the Earth. And that's the sort of scale. They're that cold. So are we ever going to see this Hawking radiation? Well, the universe is expanding. There is this 2.7 degrees absolute temperature in the cosmic microwave background. As the universe expands, the temperature goes down and down and down, and it will get colder than even the coldest black holes around. And when that happens, those holes will be now the hottest things around. And so they will radiate energy, and as they radiate energy by Einstein's E equals mc squared, they will radiate mass. So the mass of the hole gets less and less and less. How long will it take? Well, I'm going to think about the biggest black holes that we seem to have around, and maybe add a bit because they'll get bigger. And how long will that take to disappear with a pop? I'm calling it a pop at the end because it's not a very big bang. Well, depends on how you measure it, but it's nothing by comparison with any astrophysical processes. How long will that pop take to come? Well, you have to think of something like what we call sometimes a googol years, 10 to the power 100, 1 followed by 100 zeros. So it's not going to be for a while. But that will be, those black holes will disappear, and when they disappear, what we have, I'm going back to my picture of the universe is not lost. Here we have our universe as before, and I'm going to put the popping holes in now. There we have, they go off pop. It's not to scale, I should say, this is sort of 10 to 100 years or so. And what do we have after they disappear? Well, I've called what I call the very boring era. It's pretty boring already when there's nothing left but black holes. I find it hard to imagine anything more boring than sitting around waiting for the black hole to go off pop, which takes up to 10 to 100 years. And nothing much else happens of any interest. But it's even more boring after they've gone pop. And I was worrying about this. I don't know why. It's a sort of angst that cosmologists have sometimes, to worry about this very boring era after everything is gone. And it seemed to me, the thought occurred to me, well, maybe it's not so bad, because who's going to be around to be bored by this universe? Well, the most prominent things around in the universe will be photons. And it's very hard to bore a photon. It's very hard to bore a photon for two reasons. One is photons probably don't have experiences, and the other is the following, which is the reason I really want to address, which is following. Okay. How do we measure the scale of things in relativity? How do we measure time? Well, time is the real key, because once you have time, you can measure distances. And in fact, the meter rule in Paris is now not much use for measuring distances. What you can measure is much more accurate at times. And there are very accurate atomic and nuclear clocks. They're so accurate, well, your GPSs depend on things like that, global positioning systems, and all sorts of things are very accurately determined because we have extremely precise clocks in nature. And these clocks depend upon the combination of the two most famous or fundamental formulae of 20th century physics. Well, of course, Einstein's E equals mc squared, and Max Planck's E equals h nu. Nu being the frequency, h being Planck's constant, and E is the energy again. So you simply, since these are both E, that means this is equal to this. So that means that any particle of mass m is an extremely precise clock. And the frequency of that clock is simply given by its rest mass, by its mass measured in its own frames. So we have, with massive particles around, extremely precise clocks. And here I have a little bit of physics for you. See, Einstein needs, for his theory of general relativity, a thing called the metric. It's usually GAB or GMU or GIJ or something like that. The G is carries 10 numbers at each point. So there are 10 numbers you need to know at each point. Now 9 of those numbers, which are basically the ratio of those 10 numbers, tell you where the light cone is. So this cone is 9 of the numbers. The remaining number is the crowding of these surfaces which I've indicated here, which are the ticking of 2 clocks here, or if you take a lot of identical clocks coming out from this point here, the first tick will be on that, second tick here, and the third tick here. So what we need, in addition to the picture that I gave you before, no, I haven't lost it. I should have kept these things in order quite quickly, and then write down fairly well. It's probably in here somewhere. Yes, that's it. Picture I showed you of space-time. Well, I showed you the cones, and that's the part that is determined by the 9 numbers. The 10th number, see I had the cones here. If I want to talk about the metric of space-time, if I want to do Einstein's theory, I need one more piece of information at each point. And those are those services which tell us the tickings of the clocks. Now, I'm showing you these pictures because there are 2 kinds of geometry here. This is the geometry Einstein needs for his general and special theory of relativity. You need to know how fast clocks tick as well as the cones. If you just have the cones and not the surfaces, that is conformal geometry. Remember the Escher picture I showed you where the fish could get smaller and smaller up in the edge? Now if I do the same idea to space-time, that means on my space-time I have these cones conceptually drawn, one at each point. If I want the full geometry with the metrics as well, the scale of things, then I put this in. But if I don't have any clocks, that's the geometry. And if I don't have any mass, that's the geometry. And in fact, it's even stronger than that, not just with particles. You see, here you imagine a photon zipping along with the speed of light. Let me go back to my picture here. Photons only sail along the cone, they never hit any of the surfaces at all. So the photon is no good as a clock. It doesn't experience time at all. You have to have mass to experience time. If there's no mass around, then it's that geometry that's relevant. And this is also true in a more technical sense. If you take the equations of Maxwell, which are the equations which describe electromagnetism and therefore describe photons, those equations are invariant under conformal scaling. So what that means is those equations don't need these surfaces, they just need that geometry. This geometry is enough to describe Maxwell's equations, how electromagnetism works. It's also enough to describe how the other forces of nature, excluding gravity, all the Yang-Mills forces which describe the strong or the weak interactions, if there weren't any mass, they would only need this kind of geometry. So that is, if you like, the justification, the physical justification I have for saying that this picture is physically one that makes sense. As you get close to the Big Bang, then you don't need to know the metric. So I can stretch out the Big Bang and the physics works just as well. If there's nothing left but photons in the remote future, again, it will be true that the geometry, that the physics doesn't need to know the metric, just the conformal structure. So if you like, it doesn't know whether it's big or small, it's completely equivalent. Okay, you need equations to make all that make sense. I'm not going to give you the equations, but there are equations that I need to make sense of that. So now, this means that I want to have a little bit more. I want to look at one of these boundaries between one and the next. And here's the remote future now. I gave you the remote past, or the near Big Bang a minute ago. And I'm afraid I'm not found the... I haven't got quite enough room to spread these things out. I think that's my excuse. Here we are. Anyway, let me talk about this one. The extremely remote future, much matter collapses to black holes, which eventually evaporate away by Hawking's process. It takes 10 years maybe. Mainly photons left. There are a few particles left, unfortunately, for the speed, electrons and things like that, which won't disappear by themselves in conventional theory. So here's where I make a hypothesis which is a little bit unconventional. Most of the things I've said up here are an unusual way of looking at things, but not unconventional physics. This is a little bit unconventional. Not entirely, I should say, for technical reasons, but I'm saying that there was a sort of anti-Higgs or inverse Higgs process which takes place in the extremely remote future, that particles lose their mass again. And this is the idea. These massless particles, infinity is nothing, so they just zip through it, and you have this infinite future as being something which behaves like a conformal space. And I was hoping to find my other picture, which I've got rather hidden somewhere. Oh, here we are. Don't worry, it's not gone. And according to Helmut Friedrich's results, this is a nice smooth surface. And here we have the remote past of the next eon, and I'm claiming, this is my hypothesis, that they match. So as long as you don't have any mass around, they fit together very nicely. Okay, so that's the picture, that's the justification I'm saying for this. I want to end by saying two things. Two things, points which might well occur to you. One is, if you see a picture like this, you might say, well, what about the second law of thermodynamics? Didn't I say that entropy is increasing? If entropy is increasing, how can it be consistent with the cycle? Well, it's going up and up and up and up. Whoops, started going from the beginning. Well, here's where I need something else. Now here, I said I've appealed to Stephen Hawking for many of the things I want here. I'm going to appeal to Stephen Hawking again, but only one of them, because there are two Stephen Hawkings. The second law of thermodynamics, how can this make sense in a cyclic universe? Well, you see, what happens when a black hole disappears? Is information lost in black hole singularities? That is what the young Hawking of 1976 said. He said information is lost. I think he was right. He was right to say that. But the old Hawking, I have a difficulty about the young and old, because the old Hawking is the later one. I think that just, never mind. This is the 2004 Hawking, where he gave a lecture where he changed his mind. He said he changed his mind, and for some reason, information is not lost in black holes after all. I really think he was right the first time, and I'm certainly using his original insight, and I simply can't follow the written argument. I don't think he's right for the later argument. You can take the quick see. If you agree with me, you take the old Hawking, well, the young Hawking, sorry. If you disagree with me, we'll have a bit of trouble. But anyway. Now, I should make a point here, that the entropy in the universe, even now, is almost entirely in black holes. It's by far the largest entropy contribution in the universe that we know. Even without supermassive black holes, you find in galactic centers. But with those huge, our galaxy has a black hole which is about 4 million times the mass of the Sun, and the entropy in that is absolutely stupendous. Now, as the black holes eventually evaporate away, they lose degrees of freedom, and as they lose degrees of freedom, your measure on the coarse graining regions, the Boltzmann definition I gave you for entropy, actually has to keep being renormalized. It's a tricky point, and I don't want to go into it here very much, but the point is that because black holes swallow information, and I think Hawking was right to say that, that means your zero entropy has to be reset every time a black hole disappears, and that resetting of your entropy zero means that the entropy, in effect, the effective entropy becomes very small. After, it's even just before the crossover, so somewhere down here, when all the black holes are gone, the entropy is back down to the value you want. It's never a violation of the second law, it's a something. It's never a violation of the second law, it sort of transcends it. Because you change your mind about what degrees of freedom you're using in your definition of entropy, what phase space you use, and all that. It's a technicality, and the idea is that actually makes it make sense. Okay, I'm not necessarily expecting you to follow all the details of that, but never mind. That is the claim that I'm making, and it does seem to make sense. The zero eventually has to be reset every time a black hole disappears because of these velocities achieved. The final point I want to address here is it true? Have I been telling you a lot of Hogswall, all this, I hope that is a translation into Russian. I'm not sure, I hope it is, but never mind. Or is there any evidence for this? Well, I've wondered about this for a while. What kind of signal could possibly come through from one eon to the next? So here, I'm imagining, here's us, somewhere in this picture, round about here somewhere, here's us. And could there be information from this previous eon which we might see in the cosmic microwave background, perhaps? And the claim is, yes, there could well be. So I had to ask myself, what is the most violent possible process I can think of which might be a signal, present a signal which could get through from one eon to the next? But here, you have to imagine that plane there is the boundary between the previous eon, which is underneath it, and our eon, which is above it. So I put it in an extra dimension here. That's us looking back at the cosmic microwave background, and here are some violent events. What are they? Well, I told you we have a big black hole, a supermassive black hole in our center, about 4 million times the mass of the Sun. We are on a collision course with the Andromeda Galaxy. The Andromeda Galaxy has a black hole in its center, even bigger. I'm not sure how big it is, but it's even bigger than ours. Now, as we collide, don't worry, it's not going to be for a zillion years, not for a while, thousands of million years, perhaps longer. And it may be that our black holes will, well, they probably won't head-on collision, but they might get close enough that they catch each other, spiral around, and then swallow each other up. That's what this picture is meant to indicate. They spiral around and swallow each other up, and when they swallow each other up, there will be one absolutely stupendous explosion in which a few percent of the entire mass energy of those black holes will be radiated almost instantly in the form of gravitational waves. Now those are ripples in space-time predicted by Einstein, and they will be sent right out until they encounter this crossover surface from one eon to the next. Now you might ask what happens then. Because of the way the equations work, and this I can't explain without the equations, because of the way the equations work, they convert themselves, the energy in those waves converts themselves not into gravitational waves, but into waves in newly created dark matter. There are these mysteries people do refer to in cosmology, the dark energy. Well, the dark energy is needed. It has to be there. It's Einstein's cosmological constant. My scheme would not work without the cosmological constant. It also would not work without the creation of new material. You have to look again at the equations. There has to be a new material created at each crossover. And that I consider to be the initial form of dark matter. Now, dark matter is apparently up there. It's something that you don't see as ordinary matter, and it's a great puzzle to particle physicists because it doesn't seem to fit in with a normal picture. It does seem to be the major contribution to the material content of the universe by quite a long factor. And where does it come from? On this scheme, it gets created every time you pass from one eon to the next. And then it has to decay away, so the idea is it gets lost. But in that, as this impulsive wave hits the dark matter, it gives a little bit of a kick, either in our direction, if it's a distant source, or a little bit away from us, if it's a closer source. And what you would see, in some sense of the word see, is things like ripples on a pond. You have to imagine a pond, that's a good analogy, with raindrops hitting that pond, and each time they hit it, they will send out a ripple, and they will look like circles. So, will you see the ripples? No, you just see in a pond, just a long mess. But if you do clever enough statistics, you might pick up those signals. Well, just 3 weeks ago or so, a colleague of mine and I wrote an article which now appears in the European Physical Journal, plus it's called, where we claim not just that we see these ripples. You see here, if you have a cluster of galaxies and then we'll hit Andromeda 1, or we might miss it the first time, hit it next time as they go through each other, sort of thing. There are some other galaxies, not too many in our cluster, but there are lots of other clusters with loads and loads of galaxies in them, and there will be these repeated collisions of black holes which will send many signals out, and they will appear on the screen to be concentric circles. So what you want to see, and I've done it rather faint deliberately here because they are rather hard to see. This is my colleague's name, Gozajan, and we claim in this paper which has just appeared that there are strong signals that there is something there of this nature which is not explained by conventional theory. Now, maybe that someone will come up for an explanation of conventional theory, but what we seem to see are concentric rings, too many for them to be just chance, and they are definitely circles, because if you squash them and look for elliptical shapes instead, you start to lose them, you don't see them. So they're genuinely circular features out there with some cause, and we claim it's a cause like this, evidence for something through the Big Bang to the other universe. So in a sense, we're seeing through the Big Bang and claiming these events in the previous universe. So the data that we use to analyze here, there's newer data now which has just been released, Planck data, and it would be very interesting to see whether these features are still there in the Planck data. And preliminarily, it does seem they're certainly still there. But it remains to be seen what other people do with these observations. Thank you very much.